Platonic solids are called after the famous ancient Greek philosopher Platon. They are regular convex polyhedrons. They are constructed by congruent regular polygonal faces with the same number of faces meeting at each vertex. So there are only 5 solids that meet those criteria. For example, you cannot distinguish the corners. They are locally all the same. It's always the same amount of edges that meet there. Here there are 3 edges meeting always. And also when you look from here, the distance to the neighbors, it's always the same no matter at which of the vertices. When you just think about, for example, a square-based pyramid, at the apex, Spitze, 4 edges are meeting, while at the base vertex only 3 edges meet there. The tetrahedron is built from 4 equilateral triangles, the cube from 6 squares, the octahedron from 8 equilateral triangles, the dodecahedron is built by 12 regular pentagons, and the icosahedron is built by 20 equilateral triangles. Let us look at an example with one of these regular solids, namely the octahedron. The task is to find the height EF here, so try it by your own, stop the film now, and here comes the result. Let us look at the first method that probably most of you have chosen. AM is the square root of this length squared plus this length squared. Well, both lengths are s half squared, and we get square root of s squared divided by 2. Using the Pythagoras in this triangle here, we get that h half is the square root of this length af squared minus am squared. Inserting for af the s and for am what we found here, we get in the end s divided by square root of 2. And then we have to multiply the whole thing by 2, since this is h half, and we get s times square root of 2. The second and simpler method is to realize that this cross section here is also a square, since we have this octahedron and it's regular, so it has to be the same like this cross section here. So we have a right angle here, and using Pythagoras we get h is square root of s squared plus s squared, so s times square root of 2. Here on the bottom you see the nets of the 5 Platonic solids, and using these nets we can now show that there can't be other solids that are Platonic. Just think about how we can show that using these nets.